So this video, still with chapter 9, we're going to look at the buffer capacity, which is just like how long when a buffer is useful and how long it stays useful, and then look at acid-base indicators, so the chemicals that work as indicators for acids and bases. So buffer capacity is just measuring how well a solution will resist the changes in pH. So again, a buffer is a mixture of a weak acid and a weak base. Either if it was made with a one component or two component method, it ends up being a weak acid and a weak base. And it resists changes in pH, having tenths of changes in the pH value instead of whole number changes in the pH value. But certain buffers are only useful at certain pH values. And then once it's possible to add so much strong acid or so much strong base, the buffer stops resisting changes in pH. Okay, so the buffer works the best, which means its capacity is the best, which means it can take more acid and base when the pH of the buffer is at the same value as the pKa of the weak acid in the buffer. So this is the pKa of the weak acid in the buffer. Okay, so if you're trying to decide what chemicals to mix together to make a buffer at a certain pH value, okay, don't just choose like acetic acid because you know the name of it. You need to choose chemicals that work well as buffers at that pH range. So what you want to do is get a list of the pKa values of acids, and you will just find an acid whose pKa value is very close to the pH value you're wanting your buffer to work with. And then that's going to be how you decide which chemicals you mix together to make the buffer. Now, this seems like a very simple thing, but it's one of those topics, or it's one of those ideas that is taught to you. It's taught to you in Gen Chem 2, but it's also obviously in this course. And then for those of you that have to go on to take biochemistry, which I'm guessing is pretty much all of you, if you're a bio major, biochem major, or a chemistry major, they just assume you remember this, that the chemicals, how you choose which acid to use to make your buffer is going to be the acid whose pKa value is at the same or very close to the pH value of when you need your buffer to be useful. So that's why most textbooks list in the appendix the pKa values instead of the Ka values in the appendix, because this is when knowing the pKa value is more useful. So you find an acid whose pKa value is close to the pH that you need for your buffer, and that's going to be the acid that you use to make your buffer, and you'll use its conjugate base as the other chemical. Buffers really only work plus or minus 1 pH unit from their pKa value. So if something has a pKa, we've used tris a lot, of 8.072, it's not going to work to make a buffer with a pH of 4.30. And that acid's not going to make that buffer. Okay, the buffer can only be useful plus or minus 1 pH unit. So that means this chemical could go down to 7 and up to 9. That's the range in which you could make a buffer with the chemical that has the pKa value of 8.072. So you really can't just make every buffer with the same chemical and want it to work. It's specific to the acidity of the acid. So the range for buffers is plus or minus 1 pH unit. And what's going to happen is if you made your buffer, plus or minus 1 pH unit from the pKa value. So if I made my buffer, and let's say that the buffer for this tris that has this, I made it as 8.50. That's my buffer, okay? But it's only going to be useful once I get to 9.072. Once it gets to a pH above that, that buffer is going to stop being useful, because what's going to happen is instead of making small changes to the pH, it's going to stop having a good capacity, which means it's going to just start rising. It's going to stop resisting changes well. So this is important. This and this are very important ideas with buffers, but knowing which chemicals to select to make your buffer and how long that buffer is going to stay useful. So this graph is just kind of giving us a visualization of the buffer capacity. So the pKa value of the acid that was used in this buffer is 5. So this pH of 5 is when the buffer is most useful, right? Which means you can add more strong acid or strong base and see small pH changes for longer. Okay, so at the top would be adding a strong base. So we can see if you add a little bit of strong base, how the pH is going to change. The y-axis is looking at the change in pH. So we would like very close to 0 changes in pH. So you can see from right there, it's going to resist pH longest. And then if we get too far over here, so like maybe my buffer starts, so this buffer made with an acid with the pKa of 5, maybe I start at 5.50 as the pH of my buffer. Well, we're gonna see increases as we increase the pH by adding a base faster than if we started right at 5. So again, this is just giving us the visualization that the buffer works the best at the pKa value, and it kind of goes to crap, plus or minus 1 pH unit from that pKa value, because these are big pH jumps. Okay, we would prefer not to have those types of pH jumps, and it's also true down here, right on the other side. So these are just a list of some weak acids, and their pKa values are right here. So this type of a table would be useful when selecting which acid to use to make your buffer. So I would be prepared to answer questions where I give you a table like this. You wouldn't memorize, you're never memorizing pKa values. But if I give you a table and a list of acids, and I say, hey, I want to make a buffer of a pH at 7. The pH needs to be 7 for my buffer. So give me what weak acid should I use? So what you're doing is you're looking at the pKa thing, and you're going to look for which acid has a pKa closest to 7. Well, if I look, 6.90, 6.99, 7.14, 6.99 is closest to 7. That would be the chemical that I would use as my weak acid, and then use the conjugate base. So be prepared to answer questions like that. Again, you're not actually mathing. It's just understanding the pH you want your buffer to be should be as close as possible to the pKa of the acid that you use. So now we're kind of switching gears to the indicators, just a little bit of background on how acid-base indicators work. So these are the chemicals that when we're doing titrations, we use for an acid-base titration. You add a drop or two and it changes color to indicate the equivalence point, or really the end point. So acid-base indicators are just a chemical that they themselves are an acid or base, which means it has its conjugate side. So like bromocresol green, which we use with hydrochloric acid, sodium carbonate titrations, has a yellow form and a blue form. Okay, the yellow form is the acidic form. It's got extra hydrogens here. And the blue form is its conjugate base. So that's the weak acid, and this is the weak base version. You can see that the hydrogen has been donated, so it's missing. So what happens is it just turns out that this chemical in its conjugate, in its weak acid form, is the color yellow. And when it is in its weak base form, its color is blue. That's just a property of that chemical. So that's why that chemical was selected to be an indicator, where the acid form is one color and the base form is another color. So it changes color at 4.7, which means it's a good indicator of when a solution has reached a pH of 4.7, because it will go from that yellow to blue color. And it takes not right at 4.7, a little bit past it, because we have to have enough to kind of have pushed it to where we see that full color change. So acid-base indicators are just themselves an acid or base who has a different colored form when it's an acid than when it's a base. Okay. It's also why we only add a drop or two, because since they are acids and bases, they can interfere with the actual chemical reaction that we're trying to do. So this is just a list of indicators. Again, not a thing to memorize, but you can see next to the indicator color, it shows the transition range, which is like the pH range that it changes color. And it shows you the acid form color and the base form color. So the best ones of these are obviously indicators where the color differences are easier to see. These red to yellow, or even so like the orange to red, like this one, those are, I think, very difficult. It's hard to make that determination of when it's yellow, when it's red, when it's orange. So the colorless to something are ideal. Our phenolphthalein, which is the indicator that you would have had experience working with, goes from no color to pink. So that's a great one. That's a typically like the initial indicator that students are introduced to. But like yellow to orange red or yellow to orange, these are just very difficult for me. But we can see that we can't use phenolphthalein for everything, because phenolphthalein only changes color at a pH of 8.0 to 9.6. What if the titration I'm doing, the end point, is not at that pH range, but it's instead over here? Well, then I have to use one of these indicators. You've got to choose the indicator that changes color at the pH range that you need it to change color at. And in the next chapter, we're going to look at these acid-base titrations in a lot more detail. So we'll be applying this acid-base indicator information then as well. But for right now, just understanding that acid-base indicators are just a chemical. When it's acid, weak acid form, it's one color, and its weak base form, it's another color. And because of that, it got chosen to be an indicator because it changes color, and we can predict when it's going to change color. So we select it in the moments that we need it to do that. So that bromocresol green, there's bromocresol green that we looked at before, the yellow to blue. So there's the pH range. So 3.8 to 5.4. It said 4.7 as the pKa value. So we can see that the range is, outside of that, but right around that. So some indicators are polyprotic acids, which means they have more than one proton they can donate. So we can see multiple color changes. So this one can go from red to yellow and then yellow to blue at different pH values. So as an indicator can do 3 color changes, which are just fun in the lab, but it can be useful sometimes too. We're going to see sometimes in the lab we use indicators not just as endpoints to titrations, but just as an idea of what the pH value is, just an overall pH value guesstimate. Okay, so that should end chapter 9.